detections. So it is true, I'm very passionate about it, as I hope you'll see. Some notes about myself. So yes, I studied biomedical engineering here at Technical. It was during my master's that I got excited with this field of using speech for healthcare. And so I continued for a PhD, and I had the opportunity to do an internship at Google. I visited the University of Bremen as a visiting researcher. And then last year I finished the PhD. Okay? But I'm still excited about the topic. So I continue as a researcher at INESC-ID. And this is about my work that I will talk to you about. And this is our cool group, if anyone wants to join. Really cool people there. So what is this field that excites me? Speech. So speech is a sound wave that encodes information. And it encodes linguistic information, which is the message that we want to convey and that we can translate into texts. But it also encodes other information, which we call extralinguistic and paralinguistic information. And this is information about, for example, the speaker's emotions or intentions. For example, if we don't understand the language, it is easy for us still to understand if a person is making a question or giving an order. There's also information about the speaker, so we can guess the sex, we can guess the age range, perhaps where the person is from, just based on the speech sounds. And there's also information about the health of the speaker. So often we can detect not only speech and language disorders, but also neurological disorders such as Alzheimer's disease or Parkinson's disease, also psychiatric disorders such as depression or respiratory disorders, for example, obstructive sleep apnea. And a big advantage of using speech is that it's everywhere and it's very easy to record just with our microphones, in our cell phones or laptops. And how can we and why can we get health information from speech? It's because the speech production process is rather complex and it entails the neurological system, the respiratory system, and the muscles and the articulators. And so we can derive measures from speech that will contain cues for the possible malfunctions of any of these systems. And the speech production process can be roughly divided into cognitive process or more muscular actions. And so the cognitive processes concern the formulation of the message that we want to convey, including the choice of the words, the tone that we wish to pass, and generating the required muscular commands. And so we can derive biomarkers or features that encode information that are specific to these cognitive processes. And we could use features such as lexical diversity, the coherence of the message, the usage of the pronouns, and these would be indicators for certain diseases. For example, lexical diversity or coherence could be used to detect dementia, or the usage of first-person pronouns could be used to detect depression. Then the muscular actions, there are three main processes. So there's the respiration. So it is the air that we expel from the lungs that is the source for the speech signal. And also it is related to how and what we want to say. For example, if I want to shout, then I need a bigger inhalation. Or if I want to say very long sentences without pauses, like I always speak, you need a bigger inhalation as well. Then there's phonation. So phonation is the vibration of the vocal folds. And then we have the articulation. And if we move the articulators, which are the tongue and the teeth and the palate, if we move them, we alter the structure of the airway. And so we can produce very unique sounds. And again, we can derive features that will be used for these processes. For example, for phonation, I put here some features that we could use, such as the fundamental frequency, and this corresponds to the frequency of vibration of the vocal folds. And then there is shimmer and jitter that correspond to perturbations in this frequency, and many others could be derived. And the thing here is that these features usually are non-specific for a single process, so they can be altered in the presence of different diseases. And so I brought here this diagram just to show you that it gets quite confusing if you start thinking of many diseases and many symptoms. Then you can derive different features, and they are all they possibly are overlapping for different diseases. And another interesting aspect to mention is that speech affecting diseases are usually risk factors for each other. So having one increases the probability of having the other. This is just some examples. For example, if you may have obstructive sleep apnea, then it can cause disturbed sleep patterns, which then in turn may increase the probability of suffering from depression. Okay, so there Sorry. Okay. So as I was saying, the literature is full of reports with very promising results on the detection of single diseases compared to controls. But we argue that it could be important to consider simultaneously multiple diseases for these two reasons that I mentioned before. So there is an overlap in the speech manifestations, and also the diseases are often risk factors for each other. However, it is the most frequent case that the data sets available focus on a single disease instead of having annotations for multiple diseases. And this is a challenge, and not the only one. So the data sets that we often work with are usually very small. They are quite unbalanced in terms of the classes because often they just represent the normal distribution in the population. They may include biases or confounding factors and so on. So this is how I structured the presentation. I will start by talking about some of these challenges of working with small data sets. And then I will cover a framework that we introduced that tries to overcome some of these challenges and is built towards the detection of multiple diseases. Then afterwards, we talk about large language models and what role they can play in these fields. And then, yeah, then there's the conclusion. Okay, so as we were discussing, the literature is full of promising results. We have here, for example, one case of 97% sensitivity for the detection of Alzheimer's disease. We also find 99% accuracies for the detection of Parkinson's. And of course, this is quite exciting. But we've seen these results for some years now, and there are not that many commercial applications. And so we argue that before these technologies can go into the market or be deployed, it is important to address issues such as the generalizability and the reliability of the results. And so, as I was saying, these data sets often have several limitations. And in this part of the presentation, I will talk about some of these limitations with concrete examples and experiments that we conducted that are more focused on raising questions rather than giving answers. Concretely, we talk about unexpected biases, and then the difficulty of translating results to new domains. And then we also ask how distinct can the data sets be and what is the impact of different recording conditions. Okay, so the first challenge, unexpected biases. And we talk about this challenge in the context of a challenge for the research community that happened for the detection of COVID-19 back in 2021 from cough signals. And so this corpus was one of the first to be made available, and it's quite unbalanced. You can see that there's much more control samples than positive for COVID samples, which is normal, but still it represented a great effort in the community to get this data organized. But the problem was we identified there was a problem in 18% of the positive samples that was not present on the control samples. And these samples corresponded to a narrow bandwidth files, hypothetically corresponding to samples that were recording at a sample rate that was smaller than usual. And just to give an idea, so this is a spectrogram. It's a representation of the speech signal in frequency and time. And on the top one, we see like the normal files, and this on the bottom were the files that had this problem of the narrow bandwidth. So immediately, it's very easy to distinguish who has COVID and who doesn't, right? And of course, this is what the models learn. These are just the results of the baselines of the challenge. And we get the dark blue is the baseline performance. And when we remove these files, the results drop nearly to chance level around the 50% of unweighted average recall. Okay, second challenge concerns the difficulty of transferring results to new domains. And in speech, when we talk about different domains, it can be, for example, different speech tasks, because it's quite different when we're reading a text, for example, it's all very structured and planned, or when we're just having a spontaneous conversation, when everyone interrupts everyone, and there is not a very logical grammatical structure. It can also be different languages or different recording conditions. And so we talk about this challenge in the context of our work for the detection of Alzheimer's disease. And we did this analysis in parallel for two data sets. So we took ILSA data set that is longitudinal. It is a data set that is spoken in German. It contains participants doing biographic interviews. And then we compare the analysis with address. This is a benchmark data set that is cross-sectional. It is in English. And the speech task is a picture description. So the participants got a picture and they just had to describe what they were seeing. And this is a diagram of our methods. We did just the usual, taking the data, some pre-processing, extracted features, normalization, and then classification with simple classifiers. And the features we extracted, so we focused on linguistic features, and these were 4 sets of linguistic features that capture semantic categories, grammatical structure, and also the predictability of the texts. And also some linguistic features. We had some knowledge-based features and also some representations of speakers. So for example, in a network that was trained to identify the speaker ID, we take these embeddings and use them for disease detection. And these were the main results that we get. Although they were quite exciting, so we got 86% for a weighted average recall in one data set and 77% on the other, and this was better than the state of the art at the time. We noticed that these results were quite different from one data set to the other. So the best features in one data set were not the best features on the other data sets. And of course, the data sets were different, as I was saying, different languages, different tasks, but still we were hoping that the features that were capturing the most important information would be stable across different data sets because they would correspond to the diseases. And so we started wondering whether we could just be capturing some data set specific characteristics instead of something that was indeed attributable to the disease. And this led us to the following question. How different can the data sets be, and how much information about the source data set is encoded in the features that we then use for disease detection? And this is important. Why? Because we could just do cross data set studies to solve most of our problems, right? We could do out-of-domain validation, which is very used, and it's a good validation option. We could also do the detection of multiple diseases mixing data sets, because if we have one data set for one disease and another data set for another disease, we could just mix them and try to detect. But what if we're just detecting recording conditions, right? That could be a challenge. And so with these different languages and tasks and recording conditions, we were worried about this. And also, this is particularly relevant in longitudinal data sets. If we have, for example, a population that we were recording over the course of 20 years, of course, the recording conditions will change. And if we take the population at a certain age, they will only develop neurological disease later on in life. So we get all the Alzheimer's with one recording conditions and the control subjects with different recording conditions. So we need to make sure how to cope with this. And to answer these questions, we took 6 data sets that are fully spoken in English and all just contain healthy speakers, and they have similar speech tasks. And for them, we extracted features that are very frequent for disease detection. And then we plot these high-dimensional feature spaces into the projection. We're using TSNE projections. And what we see is that each data set that is represented by a different color was plotted to a different region of space, and this happened mostly with DG maps and compare. These are knowledge-based features. And then this was just more or less understand the data distribution. And we computed some supervised learning experiments. So we took these features and we tried the 6-class classification task, basically just to detect what was the source data set based on these features for disease detection. And we saw this is very, very easy to compute. So we get results in the 90s of an weighted average recall, while we'd hope it would be closer to chance level, around 17%. And even if we just do unsupervised experiments, so we just take the data and cluster it blindly in 6 clusters, we see that data just naturally clusters around the source data sets. For example, here the cluster 4 is all addressed data there. So yeah. And we did the same for here. This is the same thing, but instead of having 6 data sets, we have ILSAT. This is the data set that I was talking about before, the longitudinal one. And they have 4 specific recording times over the span of 20 years. And we also see that data just clusters around the recording time and also by gender. And so these results clearly show that the features we are using contain a lot of information about the health status. And so we need to be extra careful for the presence of unexpected biases, especially when we're using non-transparent pipelines, because we can be absolutely sure if we are detecting properties that are related to the diseases or just data set specific characteristics. Okay, so in an effort to overcome these limitations and to work towards a more reliable models that could be interpretable, we started thinking, can we just characterize the speech of a reference population and have this characterization independent of the data set? And then if we have this definition of what is healthy speech, perhaps we can identify disease signatures. Yeah, and so this made us to work towards our framework that has two parts. The first part is the reference speech characterization. That is what I was talking about. And then we leverage this reference speech characterization to try and detect speech affecting diseases in an interpretable manner. So for the reference speech characterization, we borrow this concept for clinical laboratory sciences, which are the reference intervals. Basically, this corresponds to the numbers that we see in blood tests, and we run the same kind of analysis for speech features that are clinically interpretable, linguistic and acoustic. And to take our reference speech characterization, we need to start with the reference population. And so we took the crowdsourced language assessment corpus, CLAC. This is a corpus spoken in English, and we focus on two tasks. Sustained vowel, which is basically a person saying ah for a long time with a comfortable pitch, and then a picture description. The person would get these two pictures and just had to spontaneously describe what they saw. It's important to mention that we hope to have a healthy speech definition and not a reference speech definition, but health is rather complex to define in absolute terms, and even perhaps harder to collect completely healthy verifiable data. And so we just focus here on reference speech, and these are people that claim to be disease-free, and we're happy with this definition for now. Okay, so we take the reference population, we do some pre-processing, we extract features, and here we focus on features that are clinically interpretable, and this is our main target. And we have 4 categories. One category that is related to the content. So when we can take things like content diversity, type to token ratio, the scores marker rate, and so on. Then we have speech rhythm. We take articulation rate, speech rate, the usage of pauses. We have voice quality, and these are jitter and shimmer. These are the features related to phonation that I was describing in the beginning. And we also have features related to the vocal tract shape, and these would be form and frequencies. We do some outlier removal. This is especially important because this is a crowdsourced data set, so we also get a lot of quite noisy recordings. And then, because these features that we're using can be affected by other things, for example, the gender or the age or the education or even the speech task, we were wondering, should we derive different reference intervals for each segment of the population or just group everyone into the same buckets? And so we conducted an analysis, and we concluded that we should derive different reference intervals for male and female speakers, and also for different speech tasks. This should also have different reference intervals. And then we finally compute the reference intervals, and for this, we basically look at the distribution and take the 2.5 percentile and 97.5 percentile and call this our reference limits. We also explore to do some dimensionality reduction with a feature correlation analysis. And then finally, we plot our reference intervals in a radar chart. And then we do this with our reference population. And then we can compare what we get with different data, different unseen speakers. Okay. Let's look at what we can get with this. So this is what we obtain only for female speakers and only for the vowel A. Let's focus first here on the reference population. So this is a radial chart. So each radial axis corresponds to one feature. And the dark, well, the shades are not so clear here, but anyway, this line here in the center is the average value, which is always 0 because these features are normalized. And then these two lines here are the reference limits, the lower and the upper bound of the reference limits. So in an ideal scenario, an unseen healthy speaker should be projected inside this region. And if this happens, all good. And if they fall outside of these limits, there's a cue that there could be something wrong in some of the processes that are associated with each feature. So we derive this from CLAC. And then we compare this with a different data set for Parkinson's disease detection. And when we take only the controls in this data set, so each speaker is a blue line, we see that they're mostly inside of the reference intervals. But now for the Parkinson's subjects, some of them are also inside the reference limits as well, but they more often fall outside of the reference intervals. And this happens in jitter and shimmer related features, which are specifically related to Parkinson's, also harmonics to noise ratio, that is this feature number 2. Here we see that it's very much outside. And yeah, and the interest, so this is just for Parkinson's, but it could be done for any other disease, targeting a feature that would be specific. And the interesting thing here is that this is, it can give like a clinically meaningful response, right? Okay, this was the first part. So the second part for the detection of speech affecting diseases, we do this in parallel for Alzheimer's and for Parkinson's, using the address data and the Parkinson's disease data. Then we have these first steps that are the same as before, like the pre-processing, extracting the same features, doing dimensionality reduction. Then we do normalization, and then we compute deviation scores to our reference population. And to do this, we explore different ways to compute this deviation. We have some measures based on the mean and the standard deviation, some measures based on the quartiles, the Mahalanobis distance, and so on. And then when we have these deviation scores, we can perform the binary classification. First, we started with some support vector machines just to get a sense of how things were going. But the classifier we propose for this framework are neural additive models, or NUMs for short. And these are fully transparent neural networks, and this is why we use them. And so NUMs basically are a linear combination of subnetworks, which are each of these subnets, and each subnet only attends to one single feature. But then they are trained jointly via backpropagation, the normal way. And it is the modularity that makes them so interpretable, because we can plot the shape function that is learned by each of the subnet and get a sense of how each feature contributes to the prediction. Okay, so the results for Parkinson's disease. The features that mostly contribute to the performance, okay, this is very small, but you can trust me, these are jitter and shimmer features. And so if we look at the shape functions that the neural additive models learn, here for jitter, so what we see in these plots, the y-axis is the risk of the disease. So it means that a higher value in the y-axis corresponds to an increased risk of having the disease. So here for higher values of jitter, it is associated with a higher risk of having Parkinson's disease. And this is consistent with the medical literature, because a higher jitter is associated with the lack of laryngeal control, which can result in this. Yeah. Okay, also, we see different lines here. So the models were trained in a cross-validation setting, so 10-fold. So we had 10 models, and actually each model is an ensemble of 3 models. So basically we had 30 models, and each line here corresponds to one model. And we see that they learn things that are a bit different from each other, which is not ideal, right? But at least if we average the contributions, we can still get the trends. And what else can we see in these plots is these pink shades in the background. So a darker pink shade is associated with more training data, and the lighter pink shade is associated with less training data in that region. So we see that often the models just diverge more when there is less training data, which would be expected, and also raises the importance of training these models with more data. Okay, now for Parkinson's disease, the features that are considered more important are others. So for example, we take speech rate and discourse marker rate. And here, speech rate, we have the same idea. So higher values of speech rate are associated with a lower risk of having Alzheimer's disease. So higher speech rate means a person speaking faster with less pauses. So this kind of makes sense. And here, discourse markers, the more discourse markers a person uses in their speech, it is associated with a higher risk of Alzheimer's disease. So notice this does not cause, right? So it's not because we say a lot of markers that we will have, it's not a causation mechanism, it's just an association property. And what else? So yeah, these results are consistent with what we expected from the medical literature. But the NUMs could learn something else if there was a different pattern in the data, perhaps explained by something else. And this is the big advantage, because it becomes transparent what the network is learning, and the research team can decide to perhaps not deploy the model if it's not consistent with the expectation, or the healthcare practitioners can make an informed decision or recommend further testing if needed. Okay. Now, the role that LLMs can play in this field of disease detection. So we all know that LLMs recently showed up and disrupted the field with their impressive language generation and understanding capabilities. And so we just had to investigate where if we just pass the speech through an LLM, can it just say if this person has a given disease or not? And so we take the example of Alzheimer's disease only. And we know that the speech of people with Alzheimer's disease is characterized by these main characteristics. So there is a reduced coherence in the speech, there is a lower lexical diversity, there is more word finding difficulties, and also usage of shorter sentences. And usually we use low-level proxy features to measure these high-level manifestations. For example, we can take the type-to-token ratio to measure the lexical diversity, or we could count the pauses and the repetitions to measure the word finding difficulties. But so what if we take the speech, pass through a recognizer, get the text, and feed it to an LLM? And we frame the problem in two ways. First, we ask the LLM just to predict Alzheimer's disease, just directly, ask for the diagnosis. And then on a second approach, we ask the LLM to annotate these characteristics here, which we call the macro descriptors. So these would be high-level manifestations of the disease that are easily associated and understandable by a healthcare practitioner. And actually, this would explore what the LLMs are better at, that is understanding text and its structure. And so we just ask them to annotate these dimensions, and then this could be fed to a binary classifier. These were the models that we used back when we run the experiments. Some of them may feel a bit outdated now because this happened so fast. But still, it gives a good impression of how things were working. Now, about the prompts, we defined 7 prompting strategies. The first 4, we query for the Alzheimer's diagnosis and also for a confidence estimation of how confident the model would be in this in its prediction. And we give different levels of context, either information about what is characteristic in the speech of a person with Alzheimer's, or information about the picture, or examples. Then we have a different prompt. So this is a different idea. Because we were afraid the LLMs would have guardrails and would stop, it would not give us diagnosis, we just asked for a fluency evaluation and use that as a proxy for the actual diagnosis. And then we have a prompt that queries for the macro descriptors and the prompt that queries for the macro descriptors and the Alzheimer's prediction. So this is just an example. We feed the description of the image, that is that speech task that the patients are doing, and then the LLM will give us a score between 0 and 1 for each of the macro descriptors. So for coherence, word finding difficulties, lexical diversity, and sentence length, and also give us a prediction on Alzheimer's and the confidence. And this is the distribution we get for the macro descriptors, just for 2 of them as examples. We see that the patients in pink present, in general, lower levels of lexical diversity and lower level of coherence compared to the controls that are in blue. And this is coherence. It's consistent with our expectation from the medical literature. And it's already got us excited because this is just the LLMs without any supervision, and they are able to get this from the data. And then we have here just the best classification results. When we use these 2 bars, when we use the large language models just as predictors of Alzheimer's, these are the results on the training set, although this is inference only. It's just to keep the sets consistent, and on the test set. So I think the results are not so bad just for an LLM saying if a person has Alzheimer's, but still there is a big performance drop between the 2 sets. So the results are not super stable and probably differ a lot. But when we use the LLMs as extractors of macro descriptors, then we get better performances reaching almost 80%. And also it's not described here, but we get less fails of the model, because often when we query it only for the prediction, sometimes it would say that it's undecided or not sure. And when we ask for the macro descriptors, we'd always get a score for each of the macro descriptors, and then we're able to get the prediction. These results here are just the baselines for this data set. That we're using conventional features, acoustic and linguistic. And here with just the 4 macro descriptors, we were able to surpass the performance. Another aspect that I think it's interesting is that the LLMs can actually gauge their own confidence level when making this prediction. So here in this plot, we just have the results for GPT-4. Well, Here on the left, we have the performance, the accuracy for the samples that the LLM was not sure or said it had a low confidence. And here we have the performance for the samples where it claimed to have a high confidence in the prediction. And we see clearly there is an improvement in the performance comparing the bucket of low confidence and the bucket of high confidence. And this is interesting if we want to deploy a model, because we could have a model just output a prediction if it's actually confident in its results. Another interesting observation is that the prompt for which we did not ask for a medical evaluation and asked for the fluency as a proxy because we were afraid of the guardrails, for that prompt, the model was always 100% confident in its prediction, so it was never unsure. And so perhaps framing the model in the medical domain can make it more conservative in its confidence estimate. All right, so that's it. Key takeaways. We discussed the importance of responsible research in speech-based health biomarkers because it's such a high-stake area of research, and this is particularly important. And so we discussed unexpected biases in data sets, transferability to the domains, and the impact of the recording conditions. Then we talked about the interpretable framework for disease detection that first does the reference speech characterization and then uses the neurodegenerative models that are interpretable for the detection of the disease. And then we explored the role of large language models for disease detection, especially as annotators of these macro descriptors. And that's it. Thank you. If you have any questions.
Thank you very much, Catarina. Any questions from the audience? Yes.
For the last slide, I think the final plot. Can you explain what
Sorry. Yes.
I'm not super sure.
Yeah. So I didn't go into a lot of detail, but we have different settings for this. So we had the speech samples, and the first step was to pass them to an automatic speech recognizer. And this is, so we had manual transcriptions, that is this block of rows. We had transcriptions generated with Whisper and with WAV2VEC transcriptions. And yeah, then the different lines are the different prompts that I presented. So this is just the GPT-4 for the annotation of the macro descriptors, but these are the different lines. Yeah, thank you. Here in address, yes. It is. It's not often not the case, but this is a benchmark data set, so they made it very, very balanced. Yeah. Yeah, very small also. Yes, yeah. 50 accuracy would be chance level. Fairly, I think maybe 52 or something, but around 50s, yeah. Yes, this we did for Alzheimer's disease only, and now we've been working with. Now we're trying to explore to do this on the acoustic part as well with acoustic LLMs. For this one, yes. Yeah.
I have a question.
It's based on your software. This synthetic
Sorry, I'm not sure I understand.
So you give the LLM, so there is
yeah. Mm-hmm.
And you make sure that these systems are very good.
Yeah, so the choice of which characteristics to use was based on the literature, and so there's already both in the medical part and also in the technological part, people are using other features that basically map these characteristics for Alzheimer's, and they're getting fairly good results. And this is also from the medical part. So even in medical appointments, there are some speech tests that pathologists do and get some information that's more subjective, but still get them a sense of the language progression. Because in Alzheimer's, it's actually one of the first things. So for Alzheimer's, it's more about the contents, although there's some characteristics about the sound as well. For example, the usage of pauses and this kind of thing. But for other diseases, for example, for Parkinson's, you will expect something more on the acoustic side. Yes, but this because these were text-based. But now we're exploring other things for other diseases. Yeah. Yeah, so for Alzheimer's disease, the language impairments are quite early on. So this is minor things. It's, for example, in Parkinson's, if you have a person with very advanced stage, you will hear it very clearly. But there are other minor alterations that appear very early on. There are studies that, for example, for Alzheimer's, managed to predict the onset of this disease about 7 years later. So before there can be a clinical diagnosis. And there's even some studies like older from the 90s that worked with the diaries from nuns in a convent, and this was in the early life, and then just mapping these characteristics, they could get some correlation with the output of future dementia prediction.
I have a question. Okay. When you extracted the did you try some sort of explainability techniques to understand where the LLMs looked at when they gave you some macro descriptor?
Yeah, no. That could be interesting. And also for the confidence, for example, first in the beginning, we were trying to look just at the probability of the token. But because we were using, in the beginning, earlier versions of the LLMs, they were sometimes a bit creative on the token they would output. So although we expected only yes or no, that was not always the case. And so our analysis was getting complicated, and that's why we did it this way. Now with the newer models, for example, with the GPT, that never happened. They were always being consistent on how they were outputting, but we set the pipeline already. But we didn't look at the parts of the text, but that would be an interesting to see whether they were looking at the correct examples when giving the scores. Yeah.
The performance of the LLM when you have the macro description versus but it's more like a comment to the question. But I also see short LLMs in the pre-processing. We have used in the past where people at home doing the speech data collection, and there are sometimes that people at home don't do the task that they are really supposed to. To read a passage or say, I owe you a yoga paper. Then there are family members in the background, etc. Whisper to see if the words or the speech that the people are doing is within like an agreement limit.
Okay.
Or like pre-processing.
Yeah, we've also explored in some pre-processing tasks. For example, we have a master student now working with verbal fluency, and these tasks people need to name words for a specific category, for example, animals. And so we've been using LLMs to make sure whether the word is actually an animal or something else. And yeah, we've also tried to use in this part as well. It is less risky probably because we can measure it better. Yeah.
You mentioned earlier right at the start of your talk, how do you actually do that? It's like model or just like
G-turn shimmer is purely speech signal processing.
Okay.
Yeah. So it depends a little bit. Should I have here, for example? I think I should have here a list somewhere. For example, okay, this is a lot of information, but when we look at content-related features like content density, idea density, these are extracted from the text with the old-fashioned natural language processing tools. right? Counting the tokens and stuff like this. Other features, for example, measuring the coherence. We take the embeddings, for example, sentence embeddings, and measure the cosine similarity between adjacent sentences. So it changes a little bit. Now, if we look at acoustic features, for example, for rhythm, to measure speech rate or articulation rate, we can do this in different ways, but we can measure the pauses. We try to identify which are the voice regions that would more or less map to the vowels, and so compute the articulation rate. And then, yeah, for jitters and tremors, this is signal processing. Yeah. So there's a lot of works that are using embeddings, and we also use it sometimes. But then there is just like fitting the for example, X vectors. These are embeddings. I'm so extending beyond very well. For example, we can have a network for X vectors. Just ignore the rest, okay? We just feed the audio signal raw, and so we train this network for identifying who is the speaker that is talking. And so we have these layers, and this was an earlier version. So then we had statistical pooling just to try, because speech is a variable dimension, right? It has this extra challenge of not having a fixed dimension. And here, so we had some statistical pooling and trying to get who the speaker was. And so then we can just take the embeddings from these layers. Now there are newer models with some attention instead of the statistical pooling, but we could also use this. The problem with this kind of approaches is that they are not transparent at all, right? So if you just use an embedding trained for something else, and then you get an unexpected bias with narrowband files, you'll just get a good accuracy and I'm not sure why. So yeah, there's always, so when you do this, it's always good to have like the knowledge-based approach together and try to understand whether there could be some flaws in there as well.
Are there any each encoded like something like this?
There are, yes. Well, I guess it depends on the task, right? For example, Whisper is pretty good for ASR, but I guess it depends a little on what you're trying to. Well, I would say it depends on what you want to do, right? Take the disclaimer as well. But yeah, Whisper is a good place to start these days.
Okay, thank you. Last question. Oh, okay. Thank you, Catarina.
Thank you.